Right, so we are just starting out with chapter 12. Let's see how much we can get of this. So as a review, what we talked about on Monday was that if you take a solute, which is usually the particulate that you want dissolved, the thing you want dissolved, and you put it in a solvent, which is the dissolving medium. Okay, in Gen Chem, it's going to be water. And if it dissolves, you'll get a solution. Right. So that was the key take-home point for Monday's lecture. And in order to become a solution, I'm just telling you this, I'm not going to really focus on it in terms of the exam, but to become a successful solution, your IMF, which is your intermolecular forces of solute and solvent, must overcome, they must overcome the solute-solute IMF and the solvent-solvent IMF. Then and only then you'll become a solution. And sometimes to become a solution, to become this, sometimes it doesn't happen so readily. If you take salt and water and stir it, it will dissolve. If you take glucose, which is sugar, and water, it will dissolve. Sometimes it needs a little help in dissolving, and that requires some heat. So that would be an endothermic solution. And sometimes to become a solution, it just happens so fast, so quickly, that it becomes exothermic. So sometimes you need to add heat to become a solution, get some help. Or sometimes it requires heat, Q. An exothermic will release heat, Q. An endothermic, you have to add heat, Q, to become a solution. So an example of something that's an endothermic solution, there's a substance called urea, which you don't know or you may not know, but it's a white powder just like glucose and just like other solutes. But if you put it in water, distilled water, it won't dissolve unless you add heat. So that would be an endothermic solution. So the IMFs for solute, solvent need heat to overcome these two guys, solute-solute IMF and solvent-solvent IMF, intermolecular forces. So exothermic releases heat. An example of this would be maybe like salt in water. It releases a slight amount of heat. Actually, if you take sodium solid, pure sodium solid, which you can't really, you have to buy at a specialized store, and you put it in water, it releases so much heat, it just like, So some solutions become a solution and release heat. Some solutions become a solution, need help, you have to add heat. Those are endothermic and exothermic. What it all revolves around, what it all boils down to is getting your IMF. Your IMF of your solute plus solvent must overcome these other two individual IMFs. So as far as testing is concerned, I'm not going to test you on this. I just want you to know that to become a solution, you have to overcome these individual intermolecular forces. Sometimes you need heat, and sometimes it happens and it releases heat. All right, so here's something else that's going to be important, and that is like dissolves like. This is something we see a lot in chemistry. You don't know a chemical, and you've never seen a chemical before, and can it dissolve with another chemical? Now, just as a disclaimer, here we are focusing on two liquids. Okay, two liquids. Okay, like oil and water. Okay, or I don't know, orange juice and water. Okay, two liquids, and then like dissolves like. Okay, so theirs are not solute, solvent. It's just two liquids. For like dissolves like, and that means a polar and ionic will dissolve in another polar and ionic. So that is called miscible. Okay, miscible means polar will go into polar, and polar will go into ionic. And then there's immiscible. Okay, nonpolar will go into nonpolar. Two liquids, like dissolves like. Oh, nonpolar go into polar. That's immiscible. Okay, so miscible means polar goes into polar, or nonpolar goes to nonpolar. So that is like dissolves like. Polar or ionic go into polar and ionic, and then nonpolar goes with nonpolar. Right? So let's take an example of these in page 3, just to tell you what I am talking about. Okay, like dissolves like. All right, I guess the answers already are here, so let's see if you can do it without looking at this. Okay. Alright, so we have C6H6, which is benzene. Okay, remember what benzene looks like? Okay, each of these points represents a carbon. And then we have some hydrogens here. Okay, so that's C2H6. This is C6H6, I'm sorry, C6H6, which is benzene. And will that be miscible or immiscible with water, H2O? Miscible or immiscible? Very good, it will be immiscible. So what is the main intermolecular force for benzene? Dispersion. Okay, what about for water? Okay, you can say polar. Polar is the right answer, but polar plus something else. Hydrogen bonding, yes. Okay. So like dissolves like tells us that nonpolar will not go with polar. So this is not going to mix with each other, so they are immiscible. Okay. All right, well, let's just go ahead. How about benzene and CCl4? Okay, CCl4. Okay, this is carbon tetrachloride. Okay, what do you think about that? Okay, even though the chlorines are electronegative, okay, they pull each other. Okay. So yes, nonpolar dispersion, very good. And what is C6H6? Dispersion, so they should mix. Okay, this is nonpolar. Why is this nonpolar even Cl, even though Cl is electronegative and it pulls? Okay, and they cancel each other out. Okay, they all pull in different directions, but the pulls cancel each other out. Okay, good job. Yeah, how about water and ethanol? Okay, water is what? polar and hydrogen bonding. What about ethanol? From the lab yesterday or on Monday, it also can hydrogen bond. So polar goes into polar. How about water and CCl4? Water polar, CCl4 nonpolar, like dissolves like. This would be immiscible. What about benzene and ethanol? Nonpolar, polar and can hydrogen bond? No. Let's get one more here. How about NaCl and ethanol? What do you think that would be? Yes is the right answer. Why is that? What is NaCl? Okay, this would be ionic. Okay, ionic. All right, so the Na plus would interact with the polar partial charges of the ethanol. Okay. All right, so this is the whole idea behind like dissolves like. Okay. So that's 3 words that we should know. Like dissolves like. Right, polar to polar, or ionic to polar, nonpolar to nonpolar. All right, so let's go into something completely different here. All right, units of concentration. All right, so I asked, excuse me, I'm not talking well today. I asked this question to yesterday's class. How many of you have had a blood test done? Okay, almost everyone has had blood examination done. And so what do they test? They test for glucose, I don't know, sodium, potassium. Okay, my age, you have to have 6 months. Got to get your blood work checked. So what they measure your ions or your glucose or whatever in concentrations. And if it's above a concentration, then the doctor worries. If it's below a concentration, the doctor worries. But the idea here, it's a concentration. It tells us how concentrated or how dilute something is. All right. So in chemistry, our concentrations are, there's many ways to say the concentrations, but in chemistry, we use molarity, okay, which is something that we've learned in Chem 1. And it's moles of solute over liters of solution. Okay, so make sure you know those units. Moles of solute over liters of solution. Okay, this is lowercase, this is capital M. Capital M. This is also called molar. Well, I have 2 molar HCl, right? 3 molar sodium chloride. Okay, solute, moles, solution is in liters. And we know solution is what 2 parts? Solute solvent, okay? Now this new one here for us in Gen Chem 2 is molal or molality. Okay, molal or molality. And this is moles of solute over kilograms of solvent. Moles of solute over kilograms of solvent, lowercase m. So on the exam, make sure you know the units. Okay, it's very simple. Okay, everybody should get the points. Don't just say moles over liter. Moles of solute over liters of solution. Okay, don't say moles over kilograms. Okay, what will you say? We have to be specific. Moles of solute over kilogram of solvent. All right, so this is molal. These are 2 ways to express concentrations in chemistry. Okay, now when you get your blood work done, and they don't have potassium or your sodium or glucose in molar or molal, they have it in, I don't know what they have it, micromolar, or I don't know honestly, but the idea is the same. It's a concentration. Okay, how much per unit volume. Okay, here this is how much in moles per unit kilogram. We also have fractions. Okay, mass percent. So what I want you guys to know as a class is that mass percent, what is a percent? What's percent? What if you get 90% on your exam? It means out of 100 you got how much? 90. Okay, right? So what if you get 100%? It's 1, okay, nothing. Okay, you missed nothing. So it's the same idea. Okay, when you multiply just that word percent, you should multiply it by 100. Okay, this signifies that you're getting a percent. If you don't multiply it by 100, it's just a fraction, part over whole. Part over whole. What's the part? Mass of the solute. What's the whole? Solution. What is solution again? I think you said it before. What is solution? Solute solvent, right? Remember? Okay, what about mole fraction? Okay, what's the part? Okay, moles of A. Okay, what's the whole? Moles of A plus B plus C plus D to however is in the solution. Okay, but it's in moles. It's in moles, right? It's in moles. So moles of A or moles of B over moles of the whatever's in the bottle, right? And what if we want a percentage? What do we do? Okay, multiplied by 100. So this fraction is just a part over whole. What would be the mole fraction of D? Okay, moles of D over what? Moles plus A plus B plus C plus C, whatever. Okay, everything. Okay, in the bottle. Okay, so these are just fractions. Okay, mass percent, mole fraction. All right, so what we're going to do now in the next set of about 3 or 4 problems, we'll do something that's a little difficult, though not entirely that hard. We're going to convert between molal and molar. Okay, this is something that's very new for us in Chem 2, okay, because we've never done this type of things before, converting between 2 types of concentrations, molar and molal. Okay, so let's begin with this problem here. All right, so we're going to convert 0.396 molal of glucose to molarity, okay, lowercase m to big M. All right, so what is our solute here? Glucose. Okay, and the formula for glucose, I'll give you this. I'll give you this formula for glucose. You don't have to memorize it. It's C6H12O6. All right, so without them telling you this, we can safely, okay, at least on my exam, if they don't tell you this, if they're vague, you can assume the solvent is water. Okay, distilled water. On the exam, when I write it, I'll make sure to specify your solvent is water. If not, you can just assume it's water. Okay, aqueous. All right, so we're going to convert molal to molar. We're going to convert. This thing blurs on me. I don't know what to do. Imagine it must be annoying if you're watching TV or something. It just blurs on you, and then you have to get it back to focus. So molal, what is molal? Okay, it's moles of solute over a kilogram of solvent. Okay. This is something we should know. Okay, we need to convert it to molarity. What's molarity? Moles of solute over liters of solution. All right, so this 0.396 molal is essentially 0.396 moles of glucose, C6H12O6, over a kilogram of solvent. We'll assume it's water. Okay? If they don't tell you, you can just assume it's water. Okay. All right. That's the functional definition, moles over a kilogram of solvent, molal. Now, this kilogram of solvent is the same thing as 1,000 grams of solvent. Yes? 1 kilogram is how many grams? 1,000. Very good. Okay, so we have 1,000 grams of solvent. Okay, 1 kilogram is 1,000 grams of solvent. All right, I'm going to take my 0.396 moles of glucose. And what is glucose? Okay, I'm going to take this moles of solute and convert it to grams of solute. Okay. So 1 mole of glucose contains how many grams of glucose? Okay, do you guys remember this from Chem 1? Remember? Okay, without a periodic table, we could still do it. Anybody remember carbon's weight? Very good, Samantha. Sam. 12, but we've got 6 of those. So I'll do 12.01 times 6. Anybody remember hydrogens? She's not using a periodic table. It's 1. Very good. So 1.01 times. So basically you're summing up the number in the periodic table. Okay, what is oxygen? Okay, we'll go with 16.01. Okay, so it's about 180.24 grams. You take that number in the periodic table and you add them up. This has 6 of those units, 12, and then 6 of those units. All right, so what's 0.396 times 180.24? Just double check my math here. 71.38 grams of glucose. I'll just do 2 decimal places. Okay, and this happens to be our grams of solute. Yes, ma'am?
Why do we have to convert it to grams if they both have the same radius?
I'll show you. I'll tell you. Okay, I'll tell you that. It's a good question. So this is grams of glucose. And what is glucose? Solute. Okay, so what do we know about solute and solvent? Okay, so we know that the grams of solution is equal to grams of solvent plus grams of solute. Okay, so hopefully this will make sense. Okay, so what is our grams of solvent? Very good, 1,000. Okay, what is our grams of solute? 71.38. So what is our grams of solution? 1,071.38. Very good. Okay, this is our grams of solution. Okay. All right, so we have our grams of solution. All right. And what we need now is liters of solution. Okay, we have our grams of solution, liters of solution. So how will we get to liters of solution? Okay, we're going to use the density. Okay, use the density. So let's go to the next page here. Okay, which is given to us in the problem. Right, so 1,071.38 grams of solution. Okay, what is the density? 1.3 1.16 grams per milliliter. I'm going to put that 1.16 grams at the bottom. Okay, 1.16 grams at the bottom. And put my mils on top. Okay, grams of solution per mil of solution. And then I'm going to convert that to liters. So 1,000 ml is 1 liter. So the grams cancel, the mils cancel. So 1071.38 divided by 1.16 times 1,000. 1.16 times 1,000. .924 liters. Okay, so just make sure my math is okay. 0.924 liters. Okay, so this is liters of solution. Okay, liters of solution. Okay, so finally, I think we can solve this problem, because what is molarity? Okay, molarity is moles of solute. What is our moles of solute? Our moles of solute is 0.396 moles. And what is our liters of solution? Our liters of solution is 0.924 liters. So, molarity is, once again, moles of solute over liters of solution. And that is 0.396 moles of glucose. Okay, I'll give you this formula on the exam. Liters of solution is what we just calculated as 0.924. This is moles over liter. Moles of solute over liter of solution. And what is this on our calculator? 0.43 lowercase m. I'm sorry, big M. 0.428 big M. Okay. You can even go 0.43 big M. Okay. And this is the answer. Okay, so 0.396 molal of glucose solution is the same thing as 0.43 or 0.428 molar glucose solution. This is the concentration in molality. This is the concentration in molarity. Okay. All right, can we do this on an exam? All right, let's do another problem here. Okay, we've got another 20 minutes or so. All right, calculate the molality of a 5.86 molar solution of ethanol, and the density is 0.927 grams per mil. All right, so now we have 5.86 moles over liter ethanol. What's our solute? Okay, we'll make our solute ethanol, and by default, what will be our solvent? Okay, without any information, we'll just assume that it's going to be water. Okay, solvent will be water. All right, so calculate the molality. Molality is lowercase m, and big M. What is big M? Molarity. So this 5.86 molar is the same thing as 5.86 moles of ethanol. Okay, over liters of solution. All right, so 1 liter solution is actually how many milliliters? 1 liter is how many milliliters? Okay, so we have 1,000 milliliters of solution. Okay, we have our density here. and we'll use this density to give us the grams of solution. Okay, we will use this density to give us the grams of the solution. All right, so 1,000 milliliters of solution. Okay, times, we'll put the milliliters in the denominator, 0.927 grams. And this is going to be the grams of solution, which is 927 grams of solution. Okay. All right, so what do we know about a solution? What are its two components? Solute and solvent. So we have the grams of solution is equal to the grams of solute plus the grams of solvent. Okay, what have we calculated already? We have calculated already the grams of solution, which is 927. Okay, let's calculate the grams of solute. Okay, we will take this 5.86 moles of ethanol and convert it to grams. Okay. So let's convert this to grams. So we have 5.86 moles of ethanol. Okay, 1 mole of ethanol contains how many grams? Okay, like before, we'll just use carbon as 12.01, oxygen as 16.01, and hydrogen as 1.01. All right, so we have 12.01. Okay, plus 3 times 1.01, plus another 12.01, plus 2 times 1.01, plus 16.01, plus 1.01. So about 46.09 grams. So 46.09 grams are in 1 mole of ethanol. Okay, so the moles cancel. What is that on our calculator? When we take 5.86 and multiply it by 46.09, I'll do that really quickly here. Okay, I'm getting about 270.1, 270, I'm trying to figure out how many digits to carry over. I will put an extra digit here. It's 270.1 grams of ethanol. And what is that? Is that our solute or solvent? Okay, this is our solute. So this is going to go right here. And then we will subtract them, correct. So taking this 927 grams of solution, okay, minus the 270.1 grams of solute, this should equal to the grams of solvent. Okay. So 927 minus 270.1, I'll do that on my calculator really quickly here. 927 minus 270.1, what do you guys get? I'm getting about 656.9. Let's put that in a different color here. Okay, 656.9 grams equals the grams of solvent. Okay, how will we convert that to kilogram of solvent? Okay, we will not multiply by 1,000. What will we do to convert it to kilograms? Right. So the conversion is this. There is 1,000 grams in 1 kilogram. Okay, so this is going to be 0.6569 kilograms of solvent. So let's remember our definition of molality. Molality, that's what we want to find. And the definition of molality is moles of solute divided by kilograms of solvent. Okay, our moles of solute remains the same as 5.86. Okay, moles of this ethanol. And we just calculated our kilogram of solvent as 0.659, 0.6569 kilograms. Okay, that comes to us from here. And what's 5.86 divided by 0.6569? 0.6569. 8.92, lowercase m. Okay, lowercase m. Okay, so this is our answer. All right, so in the previous problem we went from molal to molar. In this problem we did the switch. We went from molar to molal. Okay, the key point here is using the density as the intermediary. Okay, it is the intermediary that helps us get from molar to molal or from molal to molar. Right, so these are a little bit difficult problems, but once you get the hang of it, I think it should be okay. All right, I'm going to have you guys do this problem, and then I'll give you the answer during the next lecture, or I'll email the solution in Canvas, so you can check your work with my work and see if the answer is correct. So this is a practice problem that you can do at home, and I'll give you the answer for that. Let's see if we can do this problem here. And let's go ahead. All right, so this is calculate the molality. Molality is lowercase m of a 44.6% by mass aqueous solution of sodium chloride. All right, so I think this is easy to determine what's the solute and solvent. Okay, what is our solute? Yes, and what is our solvent? Okay, aqueous. Aqueous tells us the solvent is H2O. Very good. Molality is lowercase m. So 44.6% by mass sodium chloride. What does that mean, mass percent by mass? Okay, it means that in 44.6 grams of sodium chloride, which is part, okay, divided by the denominator, which is whole, part over whole, this would be 44.6 grams of sodium chloride, okay, plus how much water? How much? What do you think? How much water is in here? How much water? Okay, it's sodium chloride and water. So mass percent is 44.6% sodium chloride. So it's 44.6 divided by 100. So how much water is in there? Or how much grams of water is in there? to get to 44.6%, it's going to be 55.4 grams. Okay, 55.4. Okay, how did I get 55.4? It's 100 minus 44.6, yes. If you take this and times it 100, you should get 44.6. All right, so this is our solvent. This is our solute. What is molality again? Okay, by definition, molality is moles of solute, so we'll convert this to moles over kilograms of solvent. Okay, what is this in kilograms? We'll move the decimal places 3 to the right, or to the left, I'm sorry, and what is that? 0.0554 kilograms of solvent, which is water. And what is the moles of solute? Okay, let's go ahead and convert that to moles. Okay. So we have 44.6 grams of NaCl times 1 mole of NaCl contains how many grams? What is sodium? I think sodium is what, 23? Okay, I think I need a periodic table for this one. All right, I believe sodium is 23 point something. All right, so sodium is about 23 and chlorine is about 35. So I know chlorine. Chlorine is 35.45. I'm just adding up the numbers from the periodic table. That's chlorine. Sodium, I believe, is 23.01. So this is about 58.46 grams in 1 mole of sodium chloride. Okay, the grams cancel. So 44.6 divided by 58.46. 0.763 moles of, I'll add an extra digit here or so, 0.763 moles of NaCl. Okay, you guys getting these calculations? Okay, hopefully my calculators isn't wrong, or my calculations are correct. Right, so we have moles of solute over kilogram of solvent, and this will give us the answer. Okay, so our moles of solute is 0.763 moles. Okay, what is our moles of solvent? 0.0554 kilograms. And what is this on our calculator? What's 0.763 divided by 0.05541? 13.77, so we'll do 13.8 lowercase m. Okay. Of sodium chloride solution. Okay, and this is the answer. All right, so we have 5 more minutes here, and all right, you guys can do this at home. I will have the answer out for the next lecture. So this will be a practice problem that you can do at home. It can also save us some time. And also to save us some more time, I think what I will do is I'm going to skip pages 5 and 6. Okay, so this you'll do at home and check the answer. Do for practice. I'll have the answer out for you by next lecture, and then we'll skip page 5 and 6 just to save some time. Okay. Yeah. All right, and now we'll start talking about colligative properties. We have about 3 more minutes. We won't do any problems, but I'll give you the equations. So each of these colligative properties happens when you add a solute to a solvent. Okay, as long as it dissolves, you'll get a solution. All right, so the vapor pressure lowering. All right, the equation is this: the new vapor pressure of the solution, and I'll give you this equation on the exam. Okay, is the mole fraction of the solvent. Okay, mole fraction. Remember mole fraction? Okay, moles of solvent over what? What plus what? Solute plus solvent, moles. Okay, so this is the mole fraction, that little cursive X. Okay, it's moles of solute. I'm sorry, moles of solvent divided by the whole thing. The denominator contains the whole thing, which is solvent and plus solute. Okay. And then this mole fraction of the solvent times the vapor pressure of the solvent neat, okay, by itself, vapor pressure alone. This is P naught. Okay, sometimes in chemistry we call it neat. Okay, my PhD mentor would say, can you give me this neat dichloro something something? Neat means vapor pressure of the solvent alone, untouched, okay, by itself. Okay, so this is the equation that will give us the new vapor pressure of the solution. Okay, so this is the vapor pressure by itself. I'll give you this equation on the test. Okay, you just need to know how to use it. Okay, this is the vapor pressure of the solvent alone. Okay, that will be given also as along with this equation. Okay, so all you need to know is how to use the equation, and you need to know the mole fraction, which is moles of solvent divided by moles of solvent plus solute. Okay, boiling point elevation, I'll give you this equation. The new boiling point, okay, the new boiling point, or the change in boiling point, is going to be this constant Kb, which is called the boiling point molal constant, times the molality. Okay, do we know what molality is? What is molality? Moles of solute over what? Okay, so this is the boiling point elevation. I'll give you this equation and I'll give you the constant. Okay, Kb is the boiling point molal constant. Okay, and it's the same thing. The new freezing point, new freezing temperature, is Kf times molality. Okay, this is the freezing point molal constant. All right, and osmotic pressure is pi equals molarity times the gas constant R times temperature T. So these are the 4 equations for each of the 4 colligative properties. We'll go over them on Wednesday. Okay, so have a wonderful rest of the day. Right on the dot, 10:50. I have impeccable timing. It was hard for me to speak today and talk.